Let's suppose we're going to roll a die, and this time, if a 1 lands face up, we're going to receive $20. If a 2 lands face up, we will receive $10. If a 3 lands face up, we will receive $8. And if 4, 5, or 6 lands up, we would receive $0. And let's say that the cost to roll is $10. And this time, when we identify our random variable, let's let x equal the return. So with our probability distribution then, the values that the random variable can take on would be 10 if we roll a 1, because we would receive the $20 and the cost to roll is 10. So the return would be $10. And that probability would be a sixth, because that only happens if we roll a 1. If a 2 lands face up, we receive $10, but it cost us $10 to play, so there would be no return there, and that probability is a sixth. If we roll a 3, we receive $8, but it costs 10 to play, so that return would be -2, and that probability is a sixth. If we roll a 4, 5, or 6, there is no payout, and the cost is $10. So that value of the random variable then would be -10. And that probability would be a half. Now, what we want to do is verify that all of the criteria for a probability distribution are met, and they are. Each of our probabilities is a valid probability, or in other words, each of these probabilities is between 0 and 1. And the second criteria is that if we add all of these probabilities up, it would sum to 1, and it does in this case. So we do have a valid probability distribution. Now, if we wanted to find the expected value of this distribution, we would do that by adding up the products of the values of the random variable and their respective probabilities. So we'd have 10 times a sixth plus 0 times a sixth plus -2 times a sixth plus -10 times a half. And when we add all of this up, the result is going to be -3 2/3. And if we were to round that to the nearest cent, that would be -$3.67. Now, what does this mean? This means that if we were to play this game over and over, on the average, we would be out $3.67. So if this game were played infinitely many times, the average value of the random variable would be -3.67. And it should be noted here that in the gambling industry, the cost to play a game and the payouts are designed in such a way that the expected value would be negative every time, so that the person who is running the game, on the average, would receive a positive return. If the player is out $3.67 on the average per play, that also means that the person running the game, also known as the house, expects a positive return of $3.67 per play of the game.